I'll now start. Yeah, you see, and I think we can start now. So welcome everyone. Our today's guest is Jakub Železný, who works now in Academy of Sciences in Czech Republic in Prague. Before that, he was also studying in Prague with me. Actually, this is how I know him. And then he was a postdoc in Dresden at Max Planck Institute. He works in solid-state physics and spintronics. He will tell you everything about it in a few minutes. So I think that's it.
Okay. Can you see the screen and the pointer?
Yes.
Okay, good. Yeah. So thank you for inviting me. It's a nice opportunity to talk to different group of people than just from our field. So I'm from the Institute of Physics, from the Department of Spintronics and Nanoelectronics, which is led by Tomáš Ingvert. And we work mainly on spintronics, and I would say in the last maybe 5 years, the main topic has been anti-ferromagnets. Originally, the group was very strongly focused on semiconductors. This has now kind of been reduced a lot, and it's now mainly anti-ferromagnets and mainly anti-ferromagnetic metals, at least for now. I will be showing not just my work, but also try to give an overview of some results from the whole department. And I'm a theoretician, but I'll also be showing a lot of the experimental results. So our department is kind of combined theory and experiment, but actually the experimental part is the bigger part. And I'll also be showing some results from our collaborators. We have actually many collaborators, but the mainly what I'll be showing is related to collaboration with the Max Planck Institute in Dresden, with the group of Claudia Felser, and with the group of Hyros in Mainz. And also some experimental results are from Nottingham, from Pete Wadley's group mainly. But usually we have a lot of collaborations because the experiments are usually quite complicated and require various techniques. So what is spintronics? So as you know, in normal electronics, what's important is the electron charge. This is kind of the fundamental property that allows for electronics. But the electrons have spin too, and this is not something that directly plays a role in the normal electronics, but it's nevertheless there. And in some situations, it can be important and it can be useful. And so this is what we do in spintronics. We kind of try to see how we could use the spin usually in microelectronics, how we could make new types of devices or more efficient devices. And so what kind of situations can we have where the spin can actually be important? So if we have a normal non-magnetic or paramagnetic material, the electrons have spin, but the spins are disordered. So they point in all directions. In total, there is no moment. In such a material also, there can be some spintronics effects. But if we just look at the normal charge current, we will see no direct role of spin. The spins will be randomly oriented. If we look at the ferromagnetic material, this will be different, because in a ferromagnetic material, the magnetic moments are oriented along the same direction, or the spins of the electrons are oriented along the same direction. So then now if we have a charge current in such a material, so we will have a spin polarized current. So the spin of the conduction electrons will be polarized in one direction, preferentially polarized along one direction. So this is kind of an analogy of a polarized electromagnetic wave, for example. And so what we can do with that? So for example, you can imagine that now we have two ferromagnetic layers, and we inject the spin polarized current from one layer to the other. And so now, if the ferromagnetic layers are both magnetized in the same direction, then the current can flow freely. But now you can imagine that now we flip the magnetization of the other ferromagnetic layer. So now the electrons would like to change the spin, and so which they can do, but the current will be reduced. And we can imagine that in the limit where all the electrons point in the same direction, and the limit when spin is conserved, and I will be talking a bit more about that later, there would actually be no transport in such a case. And these kind of devices are called spin valves or magnetic tunneling junctions, depending on. So this spacer layer It's non-magnetic, just to separate the two magnetic layers. This can also be insulating, which then makes the effects larger. And then this is called the tunneling junction. This has been discovered, I think, in the, I don't know, 30 years ago. And in 2007, Albert Fert and Peter Grunberg got a Nobel Prize for this. And the reason why this was such a big deal, that this is discovery, is that this can be a quite useful thing. And this was kind of first, I would say, real Spintronics effect that was discovered. And so what this allows is to have a large magnetoresistance signal. So what we call magnetoresistance is in here is the change in resistance between when the junction is parallel and when it's anti-parallel. And this was originally quite small, but already big enough to be interesting and useful nowadays in devices that you would actually use. So for example, this is used as a magnetic field sensors in hard drives that you actually, if you have RF in your computer, it's based on this sensor. You will have a couple 100% effect, can be even larger in principle. What's also interesting about this is that this is an example of a nanotechnology, because for this to work, you need to have very thin layers, because if the layers were thick, then the same principle works, but then the resistance changes would be very small. So you really need to have a couple nanometers thick layers, ideal. Now, so this is a magnetoresistance, and this you can use as a magnetic field sensor, for example. Another effect that exists in these same devices is now, if you imagine there is some current flows through even when they are not parallel, and the spin polarization of the electrons in the second layer has to orient with the magnetization of the second layer. And this means there is a torque. There is a torque acting on the electrons, on the conduction electrons, but also there must be the same torque or the opposite torque acting on the magnetization. And so there is a torque acting on the magnetization of the ferromagnet, and this is induced by the electrical current. And so, we say it's a current-induced torque. It's called usually spin transfer torque, because in this case, it originates from transferring of spin from one layer to the other. And now what we can use this for is to switch in these junctions between a parallel and anti-parallel configuration. So we now have basically a memory device. We can switch between a junction which is in a state which is between parallel and anti-parallel state. We can read this and we can do this electrically, and we can also read this electrically by just measuring the resistance. So this is kind of a basic memory bit. And this is really used in actual memories. These memories are not really at this point used much in the real world, but they are being very intensely developed and quite close to market. At least the companies always say that. And some of these do exist on the market. So this is kind of where the Spintronics applications, I would say, got the most far is with the memories. And these have some advantages. I don't have time to go over that, but they have some advantages over other types of memory. So these are thought to be eventually used as a replacement for normal RAM memory in your computer. One advantage they have is that they are not volatile. So if you shut the power off, this will keep its state, whereas the normal memory, the operational memory that you have in your computer needs the electricity to operate. I just want to mention here also another type of effect, just as an illustration of what we can have, so that we don't necessarily have to use magnetic materials, but also in non-magnetic materials, we can have a spin current. So this is an effect which is called spin Hall effect. And what happens, and this is a relativistic effect, it happens because, well, I guess going to why this happens is maybe a bit more, is a bit involved. But the main point, what I just want to say here is that when we apply electric field in any non-magnetic material, actually, there will be a transverse spin current. So what happens is that electrons with spin up will get transmitted to the left, electrons with spin down to the right. And so then we get a pure spin current, which is transverse to the charge current. And this is often mentioned as an analogy of the Magnus effect, which is when you have a rotating body moving through a medium, you will get a deflection depending on the direction on the sense of the rotation. And so this is kind of a similar spin. Of course, it's not a rotation, but it's something similar. And so depending on the direction of the spin, you get the deflection. And the Magnus effect, it's something that's used in football, for example, to curve the trajectory. And so this shows that we can have spin currents even in non-magnetic materials. So spintronics is not necessarily limited to magnetic materials. And I cannot give here an overview of spintronics. I just wanted to mention that the applications of spintronics are not necessarily limited to memories, which is what has been done so far. But people are thinking also about many other directions. But one which is very promising in my opinion is for computing, not just for memories. And one reason why this is nowadays very, very relevant is because the Moore's law is predicted to end quite soon. So as you know, Moore's law says that the number of transistors on a microchip doubles approximately every 2 years. And this is a plot showing that this has really held true for almost 50 years. It has slowed a little bit in the last maybe 10 years, but still there has been an exponential growth, which has really been, I think, very remarkable. But this will end within a few years because the technology is reaching its limits. Its physical limits, basically. It's approaching the atomic scale. And in fact, the speed of the individual processors have not been growing for a while now, and this is mainly because of heat issues. And because of this, there is now a lot of interest in different technologies, and spintronics is one of the main directions that's kind of talked about as a replacement for the normal silicon. Now, what we do is our department, I would say, is not really applied physics. We do something that's still mainly fundamental research, but we try to do things that are motivated by potential applications. So we don't necessarily do things that are directly applied, but we try to do things that could be maybe interesting eventually. And as I said, the main thing we have been working on lately is anti-ferromagnetic materials in spintronics context mainly. So anti-ferromagnets are magnetic materials where we have a long-range magnetic order, but no net moment. So for example, this is an illustration of a simple anti-ferromagnet where the moments from the neighboring atoms will cancel out, but we still have a net moment. Now, the difficulty with anti-ferromagnets is that they are not very sensitive to magnetic fields, and they generate no net moments, which means they are very hard to study. And it's also kind of hard to see how they could be useful, at least before spintronics. And they are hard to study because the anti-ferromagnetic order is hard to detect because it generates no net moment, and it's also hard to control because it's not sensitive to magnetic fields. And there are methods that can be used for detection of this moment, for example, neutron diffraction, or there's various X-ray spectroscopy techniques, but they are quite complicated. They require big facilities. They're not easy experiments to do. And because of this, the anti-ferromagnets have been not very intensively studied. They have been known for a while, but they have not been the main focus of study. But this has really been changing in, I would say, the last maybe 5-10 years. And the big reason is spintronics. And so anti-ferromagnets actually are potentially quite interesting for spintronics. There are various reasons for that. One reason is that we have actually quite a big spectrum of anti-ferromagnetic materials that are available. So ferromagnets are usually metals. With anti-ferromagnets, we have a lot of semiconductors or insulators, even superconductors. So we have various types of materials that may be hard to get with the ferromagnets. Another thing that's actually very interesting for us is that the magnetic dynamics of anti-ferromagnets is very fast. It's much faster than a ferromagnet. So if we're looking at the speed of, for example, of the switching of the magnetic order, this would be several orders of magnitude faster in normal anti-ferromagnet than in ferromagnet. And that's, of course, something that's immediately interesting for devices. Another reason is that we have a large kind of spectrum of magnetic orders that can be anti-ferromagnetic, and there's no necessary reason. I'm showing here just illustrations of what can exist. And there's no reason why complex magnetic ores like these would necessarily have to be antiferromagnetic. They could also have a net moment. And these are certainly also interesting. But actually, it turns out very often they are antiferromagnetic. I don't really know why, but at least the ones that are known very often are antiferromagnetic. And it seems to be very common among magnetically ordered materials that they actually are antiferromagnetically. Here I just want to do a little sidestep before talking about actual results. Why are we interested in magnetic materials in the first place? And so it's kind of intuitive that if we want to do spintronics, we want to do magnetic materials, but there are actually a bit more kind of fundamental reasons why magnetic ores are, why magnetic ore materials are interesting. So one reason is, of course, from practical perspective. We can use the magnetic ore to store information. For example, by the direction of magnetic ore, we can store information and kind of give us another degree of freedom to play with. But there is another quite fundamental reason, and that is that the magnetic ore breaks time reversal symmetry. And so, because spin is a type of angular momentum, it is odd under time reversal. And this means that if we have a magnetically ordered material, it breaks time reversal symmetry. What this means is that it is essentially a spontaneous symmetry breaking. So we have a system where the interactions, of course, we don't have any weak interactions, or not in any significant way. So the interactions are time reversal invariant, but the ground state of the system breaks time reversal symmetry. And this means that we can have more effects than in a non-magnetic material. And this is something that's really quite fundamental. That basically, the less symmetries you have, the more effects you can have, because symmetries can prohibit some effects. Now, in antiferromagnets, the time reversal symmetry is also broken. But also, it is true that in many cases, we have, for example, in this kind of simple antiferromagnet, if I do a time reversal, you can see that if I then do a translation, this would be a symmetry of the system. So time reversal itself is not, but time reversal plus translation is, which then means that some effects would be prohibited by this. And I will talk a little bit more about that later. Also, I wanted to very quickly explain, just give you an idea about how we actually describe the condensed matter materials theoretically. And this is, of course, a complicated topic. So I'll just to give you an idea. This is a quite complicated problem, and the reason is that we have a quantum system and we have a very large number of interacting particles. And this really makes it almost, I would say it's essentially impossible to solve so we can describe it by basically Schrödinger equation or Dirac equation if we need relativistic effects. We don't necessarily have to do quantum field theory. Sometimes we, of course, also do, but we have conserved particles, so we can just do it, let's say, Schrödinger equation. But still, solving that directly for actual materials is almost impossible. It can be done for molecules, has been done, I think, for very simple solids. But it's essentially impossible, because if you just think about this, even just the wave function is so complicated object, because if you have 100 particles, wave function is a function of 100 variables, and that makes it insanely complicated object. And if you just write this down, you will see that even if I have hundreds of particles, it's basically possible to directly store this object on a computer, because it's just so complex. So we have to do various approximations, and the one that we use mainly is density functional theory, and I'll just try to give you a little bit of an idea about what that means. So we start with the Hamiltonian. This is just a normal Hamiltonian of non-relativistic interacting electrons. So we have kinetic energy, the Coulomb interaction of the electrons. So we assume the nuclei are static. So we have just the electrons that are in the potential of the nuclei, and the electrons are interacting through Coulomb interaction. And as I said, directly solving that's in most situations not possible. So what we do, and the idea behind density functional theory, is that we, instead of solving the interacting system, we find some non-interacting system by which we represent the system. This is called the Concham Hamiltonian, and this is basically chosen in such a way. This is a non-interacting Hamiltonian which has the same ground state density and energy as the real interacting system. It can be shown that such a Hamiltonian always exists, at least in principle. Basically, as you see here, we replace the potential by a different potential, which now depends on the density. And here, this is just the normal potential. This is hard-3. This is just the basically classical part of the Coulomb interaction. Now here we have the exchange correlation potential, and this is now what kind of contains all the complications of the quantum Coulomb interaction is contained in this. And basically, you can show that always you can find such a potential that gives you the proper ground state density. Now, another complication is that actually you see this potential depends on the density. This is a functional of the density, but the density is what we're trying to find. We don't know it. So what we have to do is we have to find a self-consistent solution. So you find with some guess of the Hamiltonian, you solve for the wave function, which is now much easier because this is non-interacting. So we just are looking for single particle wave functions. This is numerically much more accessible. From the wave functions, we get the density. From the density, we get the new Hamiltonian through the potential. And we have to find basically a Hamiltonian that gives you that, where this is self-consistent, where the density gives you the same Hamiltonian you started with, which we do through some iteration. So that's not such a huge problem. And this approach is really very useful. It's really widely used. I mean, the original papers on this have tens of thousands of citations. There's thousands of papers on this. It's used also very much in quantum chemistry, and in fact, the Kohn and Chang got the Nobel Prize in chemistry for this, not in physics. But it's also widely used in physics. It also has big limitations because one big problem is that this exchange correlation potential, that's really a formal object. We can show mathematically, we can show that it must exist, but we don't really have a way of directly expressing it. And I don't think there's really any hope that we would find any expression for the actual exchange correlation potential. We have to make very drastic approximations because this object must be incredibly complicated because it must contain all the complications of the quantum interaction in one functional. But it turns out that even quite simple approximations of these actually give, in very many cases, very useful results. Another thing is that the only thing that we are guaranteed, even if we have the correct exchange correlation potential, the only thing that we are guaranteed to obtain correctly is the ground state density, which actually is not very interesting. That's not a very useful thing to have. I mean, you could see something from that, but it's not that useful. And the ground state energy, which of course is very useful. But what we actually are doing always is that we are assuming that this Hamiltonian itself is somehow an approximation of the real Hamiltonian, and that these wave functions are some approximations of the actual wave functions. And that works very well. I mean, very well. I mean, it's quite useful in many contexts, but it's not theoretically justified. It's just something we do because empirically we know it works. And so, of course, you see people often say that that this is a first principles technique. We don't make any, we don't have any adjustable parameters, and that's true. But in many ways, this is also very much an empirical technique because we simply use it because we know it works, and we can't really show. Formally, we can't really show proof that it has to work. Another thing that I wanted to mention here is that many effects that I will be talking about are relativistic in origin. And the reason why that's important is that if we do a non-relativistic limit, so we just use the Pauli equation or Schrödinger equation, the spin and the orbital degree of freedom are decoupled. And that's, of course, very important for spintronics. And in practice, they are not decoupled, and this coupling is very important. And this coupling is called the spin-orbit coupling. And this is, so what I write here, this is the first order relativistic correction to the Schrödinger equation, which, as you can see, couples the spin to the lattice and to the orbital degree of freedom as well. So many effects that I will be talking about originate from this spin-orbit coupling. So now I get finally to the Anti-Ferromagnets Spintronics, which is what we do. And so this is the main topic of the talk. So as I said, the antiferromagnets are tricky because the antiferromagnetic core is not easy to detect and to manipulate. But I also showed you that in the newest types of ferromagnetic memories, we use these kind of junctions, which don't use magnetic fields at all. The reading out the state is done electrically, so the switching is done electrically, and their detection is done electrically. So the magnetic fields are not directly used. And so that gives us kind of a way how we could maybe do things with antiferromagnets. We just use spintronics techniques like this electrical current-induced torques rather than magnetic fields. Well, unfortunately, things are also not so easy, because if we take simple antiferromagnets, there is the electrical current is not actually spin polarized, and the reason is easy to see. We simply have two sublattices, and each gives, you can imagine that each would give you an opposite spin polarization of the current. So in total, there is no spin polarization. So these kind of devices, at least in simple antiferromagnets, don't work really. We have to do something else. For detection, there are various techniques, and I don't want to go too much into detail. Basically, you can even just take, if you imagine, if you just rotate the L order, the antiferromagnetic order 90 degrees, there will be a change in resistance. This is one example of effects that comes from the spin-orbit coupling. This is a small effect, but still you can use it to detect some switching, and I will show you some experiments where this is actually done. There are ways how to make this larger, but I don't want to go into that. But the more complicated thing is how to manipulate the antiferromagnetic current. This is something we have been working a lot on. And so the effect we have proposed to use for this is sometimes called inverse spin galvanic or magnetoelectric effect. Basically, what we have is simply, even in a non-magnetic material, we apply current and we get some magnetization. So basically, it's a current-induced or electric field-induced magnetization. And I'll try to explain a little bit why this exists. So what we need is actually a crystal that breaks inversion symmetry. The reason is that we are always in a linear regime. So the magnetization or the spin that is generated is linear in the electric field. But spin is invariant under inversion, whereas electric field changes sign under inversion. And that means that in an inversion symmetric system, we cannot have these quantities to be proportional to each other because they transform differently. So we need a crystal with broken inversion symmetry. Here I'm just showing one example. In this crystal, the inversion symmetry is broken because if we do inversion, this atom transforms into this one. And so then, because they are different, this breaks inversion symmetry. And just to see how it can happen that an electrical current generates a magnetization or some spin in a system like this. So in a solid material in equilibrium, the electrons are not actually static, and that's a consequence of quantum mechanics. They are moving in all directions, and this cancels out. So there is no net current in equilibrium, but the electrons are nevertheless moving. What I'm showing here is how the spins of the conductions electrons can look like in a system with spin-orbit coupling and broken inversion symmetry. So this is showing based on depending on the direction of the motion. So here, for example, if you have an electron that's moving in this direction, it would have a spin polarized along y direction. Whereas if it's moving along y direction, it's polarized along -x. So there is this kind of spin texture. But when you apply electric field, what happens is you get some redistribution of electrons. You have now more electrons that move along the direction than that move in the opposite direction, which is what gives you the charge current. So you have no more electrons that move to the right. But you see in this case, when you have this kind of spin texture, this also gives you now some net spin. So if you now integrate spin here, that gives you no net spin. It integrates to 0. But here, because of this redistribution, it does not integrate to 0, gives you some spin accumulation. You can imagine if you have a magnetic material, if you have this kind of effect, so you have some magnetic moments there, and by current you induce some additional magnetization, which is oriented along a different direction. Now they will try to be oriented in the same way. So again, there will be a torque induced by current, and this torque is called a spin-orbit torque because it comes from spin-orbit coupling. But the main thing is this is something that's induced by electrical current. We apply current and we get a torque acting on the magnetic moment. If it's large enough, we can switch the magnetization between two directions. And this has been done in ferromagnets. In anti-ferromagnets, we have another complication. And this is, so as I said, the magnetic fields are not very effective for manipulating anti-ferromagnets. And the reason is simple to understand. So imagine you have two magnetic moments. You apply a magnetic field. Basically, the effect of the magnetic field essentially cancels out because one of the moments would like to be oriented in one direction, the other in the opposite. So magnetic field does not really do anything. What you really want to manipulate the antiferromagnet effectively is to have magnetic fields which is opposite between the two sublattices. Now, this is not something you can actually do with external magnetic fields. You can't really generate a field that would change sign on the atomic scale. What you have to do is to generate such a field internally. And this is something which we can now do with the spin orbit torque, and this is something we have proposed already in 2014. So we consider the material like this, so you see it's a layered material. And because of the structure, it breaks inversion symmetry. You see, if I look at this structure, for example, the inversion symmetry is broken. And the reason why it's broken is because the layer above and the layer below are different. So I will have an effect like this here on this layer. But if I take the other layer with the opposite magnetic moment, you see the inversion symmetry breaking is opposite, because the layer below now, you see for the purple layer above is the gold and the layer below is the red. But for the red layer is the opposite. The layer below is gold, layer above is purple. So the inversion symmetry breaking is opposite, and because of that, also the magnetization that gets induced by the current is opposite. So we generate something like this. We get some effective magnetic fields. They are not real magnetic fields, which are opposite. And then we propose this could effectively manipulate the magnetic order. This has been observed experimentally. This was a little different material, but the symmetry is basically the same. And because, as you see here, the induced magnetization in a material with this kind of symmetry is perpendicular to the electrical current, so then you would also expect the magnetic order to switch 90 degrees. So we proposed a device like this where you apply current along one direction, the magnetic order switches 90 degrees, so switches to this direction. And then if you want to switch back, applying current along the perpendicular direction, and you switch back, and you can see here how it looks in practice. So these are the changes in the resistance as you apply, so the red dots are pulses along this direction, and the black dots are pulses along this direction. You see these changes in resistance. So this was a big result. We showed that we can manipulate the antiferromagnets effectively by electrical current. So the current density, you need quite large current densities, but it's something that can be done experimentally. This is something that you see was done in 2016. The experimentalists in our department have been working on this kind of switching since then. It's really been maybe 5 years of work. And I have to say, we still don't really understand fully what's going on. So what I presented here seems kind of a nice, clear picture. In reality, it seems that and we thought for a while that this is really the full story there. It turns out things are more complicated. This mechanism I said there exists, but there's also some other mechanism that's not fully understood. One complication that we have there, which is actually always present in magnetic materials, is that the magnetic order is not uniform across the whole device. You have magnetic domains. So this is an illustration of how it looks in an antiferromagnet. So you have regions where you have one direction of the order parameter, and then in a different region, the order parameter will be, for example, opposite or 90 degrees rotated. So you see here the moments are rotated by 180 degrees compared to here. This is something that naturally happens in all magnetic materials. Here, this is a picture. So this is a microscope, basically X-ray image, showing the white color here means one direction of the null vector of the antiferromagnetic order, and black means a perpendicular direction. And you see that when we apply current along one direction, we get whiter image. Along one direction, we get the darker image. That means we have switched by 90 degrees. But it also shows it's not really uniform. There are domains. The resolution is not very good. It's hard to see what's actually going on. But it's clear that it's not a single domain. And that makes things more complicated. And in fact, it turns out that there is another effect going on, not just rotation by 90 degrees, but it turns out that the current actually also, what it does is it breaks up big domains into small domains. So you see it here. This is before applying current, or big domains. After current, it's kind of a mess. It's hard to see what exactly is going on. There's also a very recent result showing that there are some strange domain walls present. So if you have the two domains, they are usually separated by a domain wall, so a region where the order parameter rotates. Usually they are quite wide because the magnetic moments don't try to be anti-parallel usually, or parallel, so don't want to have big angles between them. So the domain walls are quite wide. In copper manganese arsenide, it turns out that there seem to be also completely sharp transition between two domains. So what you see here, this is an illustration. So you have one domain here and the another domain here. You see the magnetic moment just suddenly jumps. We don't really understand why that would happen. It seems to be something that was not really observed in any magnetic systems before. It maybe is playing a role for the switching. I just want to show this here in that things are often quite complicated, especially with antiferromagnets. So we still don't really understand what's going on. On the other hand, it's clear that the electrical signals that you then detect are actually quite interesting. In particular, you see the switching signals are quite large. So there is maybe 20% change in resistance after applying the current pulse, which may not seem like much, but this is actually quite hard to achieve. This is just a single layer material. If you have the multi-layer, the junctions I was talking about in the beginning, it's easier to have large effects. But this kind of effect in a single layer material, that's not easy. And it's not, we don't really understand where it comes from, but nevertheless, just from kind of an application perspective, it seems interesting. It's a big signal. Furthermore, you kind of see, you can switch by applying more current pulses, you can switch progressively, create bigger changes in resistance. What you see here also is that kind of depending on the magnitude of the pulse and the timing, you see different changes. So it behaves, and you see also relaxation. So you switch, it starts to come back kind of on a second time scale, which is not something you would want in a memory, but actually in some kind of applications that may actually be useful. And in particular, lately we have been thinking about neuromorphic computing. So I'll just briefly explain what this means, where this could actually be also interesting. So as you probably have heard, in maybe last 10 years or maybe longer than that, there's been a huge boom in machine learning and deep learning. So algorithms which are based usually on these artificial neural networks. So these are software algorithms that are used for pattern recognition. And they have been extremely useful because pattern recognition is very hard to do on a computer. And this was really a breakthrough. People have found out that in this way, this can be done. And this is now widely used for all kinds of like image recognition or speech recognition, Google Translate. And this is an algorithm. It's used. It's done by software, so you use normal hardware. But actually, the algorithms are kind of inspired by how the brain works. But people are also trying to do this in hardware. So the artificial neural network, that's basically it's kind of a structure which contains neurons, and they are connected by the synapses. And basically, you can have different weights on the synapses. And then I don't want to go into details, but basically the idea is that you could also create something in hardware where you would create an artificial neuron, artificial synapse. This would have some advantages over doing it in software. It would be in principle much more efficient. And these properties of the copper manganese arsenide were kind of gradually changed to resistance. That's something which is actually interesting for the synapses in principle, or is kind of the property that the change in resistance depends on the timing of the pulses, on like how far apart are they, or even on like which comes first. This is something that in brain actually very important. And so there are now ideas that this could be interesting for this neuromorphic computing, and this is really a huge field now. I have been telling, I think, for quite long, but I will try to quickly just tell a little bit more. So I've tried to summarize a bit about what the group as a whole has been doing. I'll try to tell a little bit more about the work I have done myself, about more theoretical work. But I'll try to be quick because I've been talking now for a long time. So as I said, in most antiferromagnets, the electrical current is not spin polarized. And the reason is symmetry, actually. The reason is that we have either a symmetry, which is this time reversal plus translation, Or in a material like this, the symmetry that prohibits the spin polarized current is a time reversal plus inversion. So in a material like this, if we do inversion, so this shows the inversion center. In a non-magnetic material, in a non-magnetic system, this would have inversion symmetry. This atom would go into this one under inversion. But because it's magnetically, inversion symmetry is broken. But you see, if I do inversion, this atom goes here. Then if I do time reversal, that just flips the moment. That will then be a symmetry. So these symmetries are actually quite important. And if you have one of these, this prohibits many effects, and in particular the spin polarization of the charge current. Now we can try to find antiferromagnets that don't have these symmetries, and the ones we have to look at first are these non-collinear systems. So these are also antiferromagnets, but you see now there is not one direction of the moments. They are pointing along different directions, but in total it still integrates to zero. Then the moment integrates to zero. And we have shown that in these systems you can have a spin polarized current. We have shown this theoretically, and this I'm not aware of an experimental observation. I hope somebody will try to measure. And then you can try to think about now the junctions like Anna have been talking about in the beginning. So again, we can have two layers separated by some spacer, and we can think about having a torque there, the spin transfer torque, or having the magnetoresistance, giant magnetoresistance like in the ferromagnetic systems. And we have tried to calculate that. We have used 2D system like this. So we have here now a system which is 2D just for simplicity, because these calculations are very complicated. But we again have one layer which is antiferromagnetic, a spacer which is non-magnetic, and an antiferromagnetic layer. And basically, I'm just showing you just as an illustration what we get. What we have tried to do is to see how the torque that's induced depends on the disorder. And this is quite important, because if you do this kind of calculation with any antiferromagnet, you actually find a torque, you find a large torque, you find a large magnetoresistance. But the real systems are not perfect. And once you have this order, in antiferromagnets that do not have a spin polarized current, it seems that the disorder very quickly kills these effects. In ferromagnets, it does not. And so we have done this with these non-collinear antiferromagnets, and that seems to work in a way that's quite similar to ferromagnets. So we see some change when we include disorder. So these curves show just the dependence on disorder of the torque. But it's kind of not drastic, and it's comparable to what we have in ferromagnets. We have done the calculation also for a ferromagnet. So this, we believe, is something that could be quite interesting, that maybe we could do the same kind of devices like people do with ferromagnets. We could do now with antiferromagnets, and maybe you would have some advantages. For example, the switching speed would be much faster. We also calculated magnetoresistance. Again, we show that it's comparable to the ferromagnets. It actually decreases a lot with disorder, but still remains even with significant disorder, and it's comparable to the ferromagnet. So we believe that this is something that would work in practice. And the last topic I want to very quickly mention is that these transverse spin currents, so the spin Hall effect. So why are these interesting? So what we have here is we apply an electrical field which generates a longitudinal charge current and a transverse spin current. And the reason why this is interesting is that what we can basically do is transform a charge current into a spin current, or vice versa. And so you can imagine this is a quite useful and fundamental functionality. And so this is something that's really widely used in spintronics. For example, as a detector of spin current, if you imagine that you inject spin current in a material through inverse, this effect also has an inverse effect that generates a charge current, which you can detect as a voltage. And for example, it's also used in a bilayer systems like these. So we apply electric field along this direction, and it generates a spin current which is perpendicular, and this flows in the ferromagnetic layer and now generates a torque on the ferromagnet. And so this is also something that's quite useful. What we have done is we have shown that in the non-collinear antiferromagnets, there is a new type of spin Hall effect called the magnetic spin Hall effect. And kind of just quickly explain why it's quite interesting. So one reason is that this is a new type of mechanism, but mainly why I think it's interesting is that this is not an effect that we can control by a magnetic order. So we have a transverse spin current, We can use it for spin charge conversion. But what we can also do is we can manipulate the magnetic core, and this controls the polarization of the spin current. And that we believe could be quite useful functionality. Another reason why this is interesting is that the origin of this is not relativistic. So the spin Hall effect has the origin in spin orbit coupling. But in this case, we do have this even when there is in the non-relativistic limit. And this is in fact something that's not unique to this kind of effect. It turns out non-collinear magnetic or breaks symmetries in a way that's quite similar to spin orbit coupling. So kind of can allow for similar type of effects. So in this way, the non-collinear magnetic core is quite interesting. On the other hand, if the non-collinear magnetic core is there, that means spin is not conserved. This means basically what this means: spin does not commute with the Hamiltonian. It's not a good quantum number. And that's also true when we have spin orbit coupling. This is something that's quite. It's not surprising, of course, if we have relativistic effects. What we should really be doing is using the total angular momentum, not spin. But that's not very easy thing to do. We like to take in terms of spin. And also angular momentum in total is conserved, but not necessarily of the electrons themselves, because, for example, angular momentum can go to the lattice, to vibrations of the lattice, for example. So this makes things tricky. And in practice, what this means is that spin currents are not conserved. They dissipate. They're not like charge current, which cannot disappear, right? And this makes some things not, this is a complication. It's a complication both for us in terms of theory, makes the theory more kind of more tricky concept in terms of theory, but also in practical terms, because if the spin currents dissipate quickly, it makes it harder to use them for something. And so we have been thinking whether we could actually get this kind of transverse spin currents for spin charge conversions, where we could do that with the system that can conserve spin. And in fact, the answer is yes. So we need a collinear system now. In a collinear system, one component of the spin, so the component of the spin along the magnetic order, that's conserved because that commutes, right? And so if we do, in a material like this, still spin is not conserved in a real system, because you still have some spin orbit coupling. You have some oscillations of the magnetic moments due to temperature, so they are not strictly collinear. But in the limit of no relativistic effects and zero temperature, spin would be conserved in a system like this. And basically, we show that still we have a transverse spin current. And we believe this could be quite interesting because, in principle, now we can think about having the spin current will still be diffusive, will still disappear after some time, but or after some length. But we believe in these kind of systems, the length could be much larger, or it survives. And in fact, here the origin of the spin current is actually extremely simple. I think this is maybe the simplest mechanism we can think of. So in this kind of system, because spin is a good quantum number, we can every electron is, we can say, is either spin up or spin down. And now, so we can talk about spin up and spin down currents. And what happens here is simply the spin up and spin down current flow at some angle with respect to each other. And this means, so the charge current is just sum of the two, so that's longitudinal with the electric field, but the spin current is difference between the two, so that will be transferred. So basically, you get a spin current just because of that. And this, I think, is really quite simple, and it seems to be very large effect. So we also believe this is quite nice, and we got the paper accepted like 2 days ago, which made me very happy. Okay, so I think this is all from me. I think this has been quite long. Basically, the message from me is that antiferromagnets are very interesting materials, in my opinion, for spintronics, but also in general. Kind of as the experimental techniques progress, they become easier to study, and I really believe they will be much more prominent in the future than they have been in the past. One reason for that is because we can control the antiferromagnetic or electrically, or also optically. This is something I have not been talking about at all, but it's something that in our group is also studied a lot. And this is potentially very interesting because people are also thinking about optics-based computing, not just electronics-based. and this has its advantages. In copper manganese arsenide, this seems to be very interesting material. The switching is very complex. Really, after maybe 6 years, we don't really understand what's going on, but seems very interesting, maybe for neuromorphic computing or maybe for other stuff too. And the final point that I wanted to make is that if we have simple high symmetry antiferromagnets, this limits a lot what kind of effects we can have. But if we look at maybe more complex antiferromagnets or lower symmetry antiferromagnets, we will have effects that otherwise would not exist. And I did not really explain here what's so special here. So in this kind of material, what's important is that you have here the magnetic atoms and you have the non-magnetic atoms. And these non-magnetic atoms you see the environment of this atom is rotated compared to this one. And this kills these time reversal plus inversion or translation symmetries, and then allows for other effects, but still it's an antiferromagnetic system with no moment. Okay, so that has been all from me. Thank you for your attention, and I would be happy to answer any questions.
Yeah, let's think for a nice talk. Yeah, it's not easy to clap our hands, but yeah, well, please, questions.
Yeah. So I have a question. That's okay.
Yeah, definitely, Diana.
Yes.
Yeah, sure.
Yeah. So I saw that in your calculations, you're using a Kagome lattice. Is that
Right.
true? You went quite quick through that.
Yeah, we do. The reason is that if you look at this manganese 310 material, if you just take one plane from that is this Kagome lattice. So this kind of where the inspiration came from, basically. But it's not based on any real system. Maybe a system like this even exists, but for us, this was really just way how to make the calculation simpler.
Okay, so it's not that you use this type of lattice and then you have to take care of all the effects on the Kagome, like restoration and coordination number.
Yeah, that's not really the goal here. Yeah, so for us, it's not even something we came up with. Other people have also been using these kind of models. It's just basically, we try to take something as simple as possible so that we understand what the simpler you make a system, the easier it's to understand where what you are interested in comes from. And so people have just been doing this. Even if you look in this system, there are also, if you look at the planes where the magnetic moments are also is this Kagome lattice. So that's why people took it. But the inspirations are these systems where, for example, I don't think these are frustrated systems, even though they are these triangular, you don't have these frustrated effects, although I don't really understand this. And so for us, this has been really just a toy model of something which kind of has the same symmetry, but it's simple enough that we can easily deal with it theoretically.
But do you have to take into account the effects of the two-dimensionality? Or do you still think of it as a three-dimensional antiferromagnet?
It's a bit tricky, right? Because basically we don't do anything with the two-dimensionality. You can do the calculation basically the same way. You're right, there are many things where if this was an actual 2D system, magnetism in 2D in general is tricky. If we would, for example, would try to understand the behavior of the magnetic ore itself, then it would probably not be a good idea to start with 2D, right? Because it behaves very differently. For the transport, we don't actually think the dimensionality plays that big role. I mean, it can still be important for some things, but on the level of what we have done, we don't think the dimensionality would be that important, because what we are after is some kind of general things. Like, for example, what we find is that you have spin current coming from one layer to the other, and you see that some part of the spin current get absorbed, and then we compare that to the ferromagnets. And for example, you see in ferromagnets only the perpendicular component to the ferromagnetic core get absorbed. In here, the whole spin current gets absorbed because of the non-collinearity. So this is a kind of general conclusion which we don't believe is related to dimensionality. And so these are the things we are after. on the other hand, you're right, dimensionality would of course play a role in some ways. And for example, I don't think the actual numbers that we get are very useful because the real system is three-dimensional, it's different, right? But this kind of general things like what happens when we put this order there? Does it stay roughly the same, or does it get reduced drastically? That's something that we don't think it's related to dimensionality.
And the
but I
spin
hope the
value, is it
referees don't
1/2?
get, sorry?
The spin value is 1/2, or what is the spin value?
Well, so in our case, we have always electrons which have spin 1/2. In this case, in this model, but the magnetic moments themselves on the atoms don't have to be 1/2. In this case, this is a kind of a model where the moments themselves are not treated quantum mechanically. They are like a mean field moments.
Okay.
So we have, so then the magnitude don't actually matter, I think. I don't.
Okay, that's where you get rid of all the solar effects. And then the solution you have in the next slide, or your results there. So, was it in
So what we
next
show here is this is a torque normalized by the current. You see, I don't give here any units, but
Yeah,
because I don't think the units are so important because it's the model, right?
What I don't understand is the x-axis. So
right, so the d, this is a parameter which controls the magnitude of disorder. We basically, the disorder will be similar, it would be something like a phonon or something like that. Again, it's a toy model, yeah. But the larger the d is, the larger the disorder is. And then the different curves here correspond to a different interfacial disorder. So we also include steps on the interface, because this is something that we believe can be quite important, because you always have them. You can't really get rid of them. At least it's very hard, I'm sure, to do that. And in an antiferromagnet, they could be important. And I think this is maybe one reason why experimental people have tried to do these kind of junctions with antiferromagnets and did not really see anything. But I have used simple antiferromagnets where I think, for example, these steps on the interface could play a big role. And so we have also included the steps on the interface. We have included a lot so that the interface is very disordered. Basically, yeah, and these curves just show how this changes the torque with respect to the disorder changes. And so you see it decreases, but not dramatically.
Okay, thank you. Maybe more people have questions. I have an extra one, but
I have time. For me, it's not a problem.
Yeah, so are there any other questions, or can Diana ask? So I think Diana can ask.
I just want to know your view of what the perspectives are on spintronics, but controlling the excitations. So spin waves or spin-ons.
I mean, this is something which, as far as I know, they do a lot in Trondheim, right? I'm not really an expert on that. It's kind of different directions, right? So what we have been doing in Prague mostly is related to electrons and mainly metals, electronic currents, or optical excitations, but still related to the electrons directly. Then another approach is to look at excitations of the magnetic core itself, like the some magnetic waves or magnons, right? I think it's for sure both interesting. I don't really know that much about the magnonics. In my personal opinion is that the way to go is to go away from metals, because in metals you always have heat dissipation. If you have currents there, this generates heat, and that's not something you want because the energy goes where you don't want it. And this is in fact the reason why with the conventional processors, why the speed of the processors has not been increasing. It's because if you increase the frequency, the heat scales with the square of the frequency. At some point, you just can't do it anymore. So in my opinion, the way to go long term is to go away from the metals. One way to do that is certainly the magnets. That's maybe the most kind of natural way. If you have insulators, you cannot have electronic currents. but you can have spin currents carried by the magnets, for example. So that in this sense, this is maybe interesting directions. We also have been thinking of how we could do it even with the electrons. For example, one way is with topological materials where you have an insulator, but then you have some conductive states on the interface. That maybe is also interesting.
Okay, thanks. So actually, one of my sample is a non-collinear antiferromagnet.
Okay, it's nice.
If you want the structure, I can tell you.
Sure. Yeah, we have been doing what we have been doing a lot now is kind of looking at different structures and thinking what kind of effects you can have, because this you can do just from symmetry. And there has been, I think, a huge progress in that in the last couple of years. People realize that the kind of phenomenology of effects you can have in this kind of system is much larger. And so, yeah, I would actually be interested.
I don't have more questions.
Yeah, are there more questions? Yeah, if not, maybe I have a naive question. You said that the response speed is much bigger for antiferromagnets than for magnets. So can this be somehow easily understood?
Yeah, this is the reason is that if you have ferromagnets and you just, let's say, apply a magnetic field, the way it is, and then the magnetic order will start to rotate to the magnetic field direction. This happens, when this happens, all of the magnetic moments in the ferromagnet stay collinear, stay in the same direction, and they all rotate together. In the antiferromagnet, this never happens. Even if you apply a field like this, which is opposite on the two sublattices, still what happens is that they will first, in a case like this, what happens, they will first cant upwards in the same direction, and then start to rotate. And then the reason why this is fast is because the interaction that keeps them parallel is very strong. And so when you cant them, this interaction comes into play. And because it is strong, it results in a fast dynamics. But in the ferromagnets, the only interaction that's important here is the interaction that makes all the moment points along some direction with respect to the crystal. So you're rotating and they maybe want to stay along one direction. So this interaction is much weaker. So in the antiferromagnets, only this one that comes into play, and the magnetic field itself. But in the antiferromagnet, this interaction is called exchange interaction that keeps them parallel. And so this is the reason, and it's quite fundamental. I think you can really show this quite, formally show that as long as this exchange interaction is strong, which it usually is. I mean, just for comparison, I mean, this exchange interaction between the spins, that's something that would be like thousands of Teslas, or hundreds for sure, in a normal antiferromagnet or a ferromagnet too. The magnetic fields that you can generate in a laboratory are maybe 10 Tesla. Like if you have very big facilities, you can do 100. So these are huge fields. So that's why, and then this is why I think antiferromagnets are really exciting, because kind of you can use these internal fields, which are huge, which you could not create with the external field. I don't know if that explains it.
Yeah, I see. Thank you. Yes. Are there any further questions?
Can I ask one? Well, it may be slightly off topic.
Definitely.
You mentioned the example of the material where you had the domain wall that was like sharp from one layer of the spins to the other. Yeah. I was just wondering if there's some way to understand this, because normally one thinks of domain wall like, it's associated with like bending energy of your Ode parameter. There's always some natural scale which is macroscopic compared to
exactly. Yeah. No, this is really a mystery, I would say. So they have done. So most of the domain walls in this material certainly are large, are on this maybe 100 nanometer scale, which is close to macroscopic scale. These domain walls were observed. Most likely, I would say, still it's 100% sure. It's a bit tricky. There is a kind of transition like this, and almost surely it's in the antiferromagnetic order parameter, because we don't really think there is any other type of order. But in principle, I think it's not bulletproof. But I think most likely it's a transition in the antiferromagnetic order. And as you say, this is something that's very unnatural. And I personally did not believe that for a long time, to be honest. But most likely it's really there, but we don't understand why. We have been trying to do some calculations. Basically, our idea is that this certainly cannot be, equilibrium state. It must be some metastable state. And this, we think, is maybe what's happening. When you apply the current, you deposit a lot of heat in your material, and you, for some reason, create this metastable state, which then slowly relax. But still, the relaxation is on a seconds or minutes. It's a macroscopic. It's 10 orders of magnitude slower than the speed of the dynamics itself. So the metastability is quite significant. We think that maybe when you make it sharp like this, somehow the material, the exchange, the interactions between the magnetic moments get modified, and this creates basically a local minima. Well, we don't really understand. It's very exciting. So this manuscript has been sent to science. In my opinion, if the referees will believe what you're saying, it can get accepted, because it's really such a new thing. We're really not aware of this being ever observed. And in ferromagnets, people would see that, because it's much easier to study the domain walls, and people have studied them for 100 years. So if this existed in normal ferromagnets, people would have noticed. So this is maybe, but in antiferromagnets, it's possible that this exists in every antiferromagnet, and just nobody has noticed, because it's really not an easy thing to see. And in fact, even the method that was used, so this is using the DM, the transmission electron microscope. This has never been used with atomic. This is used commonly with atomic resolution, but then you can also. They use some tricks to also get sensitivity to the spin, and this is done, but never has been done with atomic resolution. So it's this kind of a very breakthrough thing. I think it's very questionable if we convince referees. Not everybody in our group is fully convinced. But yeah, I really don't have an explanation.
Okay, thanks.
Okay, thank you. So are there any further questions? Yeah. So if not, I suggest to thank the speaker again and stop recording, but we can continue the discussion. Yeah. So thank you very much once more for a nice talk. I'll stop recording.